Okay, good morning to all of you. Today is our last lecture in the vector calculus, the Stokes theorems. Recall back, okay, your vector field F in two dimensions. Let the F is mi plus nj, and the vector value functions, okay, rt is a xti plus ytj. Okay, dr, okay, will be okay, ddt your xt or dxdt in component I, okay, component j ddt your yt, which is dy dt. So actually you have dr dt, so dr bring to right hand side. Okay, later on dt here cancel. So dr also equal to dxi plus dyj. Okay, and recall back, okay, the line integral of vector field. Line integral of f dot dr along the curve C defined by the vector value functions rt is xti plus ytj. Okay, to evaluate the line integral of scalar vector field, okay, to do the vector f, mean the mi plus nj dot with dr here, which is dxi plus dyj. Once you get integral of m dx plus n dy. Okay, recall back in the previous lecture we have shown that the line integral of actually differential form is equivalent to the line integral of vector field. Okay, and recall back, okay, your Greens theorem, okay, Greens theorem, where the integral of m dx plus n dy, okay, where you have the piecewise, you have a simple closed piecewise smooth curve, okay, curve C oriented counterclockwise. If your mxy and nxy have continuous first partial derivative on some set containing the region R, okay, in line integral using the Greens theorem, last time you have learned the integral of m dx plus n dy, okay, along the curve C, along the curve C. And if the curve C is closed, okay, and oriented counterclockwise, so it's closed, oriented counterclockwise, then instead of you break your, okay, because it's piecewise smooth curve, instead of, let's say you got the triangular curve, so you have three curves, then you have to do it C1, C2, C3 three times. However, if the curve is closed and in the okay, orientation counterclockwise, then you can use the Greens theorem. Okay, by the Greens theorem last time, mean the integral m dx plus n dy, okay, along the curve C, which is closed and oriented counterclockwise, is actually equal to the, using Greens theorem, is equal to the double integral del n del x, okay, delta x coefficient of dy minus your delta y coefficient of, okay, dx, mean del n del x minus del m del y dA. This last time we learned in this form, the Greens theorem. Okay, and actually del n del x minus del m del y is equivalent to the curl of f, By the curl of f is two dimensions, curl is a 2D okay, differential operator, delta xi plus delta yj. Okay, so this is y. Cross with vector f, which is mi plus nj. Okay, hence you get del n del x minus del m del y. So means the Greens theorem here is actually equivalent to the double integral del cos f dA. This is the Greens theorem. Last time, if we want to evaluate the line integral of differential form, where the curve C is simple, closed, and anti-clockwise, then you can evaluate the double integral of del n del x minus del m del y dA. Okay, because the curve C is closed, then you can form the region R. That's why instead of evaluate the line integral, you evaluate double integral dA over region R. And this del n del x minus del m del y is actually equivalent to the curl of f dA. Okay, in this case, your curve C is in two dimensions. However, okay, if your curve C in 3 dimensions, okay, curve C is 3 dimensions, and you want to evaluate the line integral f dot dr, okay, it's actually f dot d. line integral f dot dr is equivalent to the line integral of differential form and to be equal to the curl of f. Okay, however, this is ds. Now, what's the Stokes theorem? Okay, let S be a piecewise smooth orientable surface that is bounded by a simple closed piecewise smooth curve C with positive orientation is actually anti-clockwise. If the component of the vector field, the F, is mi plus nj plus pk are continuous, okay, and have continuous first partial derivative on some open set containing S, then the line integral f dot dr, okay, meaning the curve C is actually simple, closed, and oriented counterclockwise, and this will be equal to the curl of f dot n d. Okay, the d capital S, this is 1 unit of the surface area. So where the curl of f is del cross f dot n ds. Okay, you compare with the Greens theorem. Greens theorems. Okay. Greens theorem. Last lecture we learned is this one, the blue color. Okay, Greens theorem normally will give in, okay, the line integral m dx plus n dy along the curve C, where the C is simple closed, okay, oriented counterclockwise, is equal to the double integral del n del x minus del n del y dA, and we have proved that this del n del x minus del n del y is actually equal to the curl of f, and we have proved it just now. Okay, the line integral of vector field is equivalent to the line integral of differential form. This equal to this and equal to this. So mean Greens theorem is actually the curve C is on 2D, okay, close, to form the region R, because it's 2D, and then instead of evaluate, okay, your curve C, for example, your curve C is a rectangular, okay, curve C, you got 4 curve, rectangular, you got 4 curve. Instead of evaluate the line integral 4 times, in the curve C of rectangular, which is closed and anti-clockwise direction, then it forms a region R. Then you can evaluate the double integral, okay, del n del x minus del n del y, which is curl of f dA, because the curve C is, okay, 2D. If the curve C is 3D, curve C now is 3 dimensions, so the f dot dr, curve C is 3 dimensions. For example, you have like this, okay, the curve C on the tetrahedron, okay, here, C1, C2, C3. If you want to evaluate the line integral, okay, using f dot dr, then you have to break the curve into C1, C2, C3, 3 times. Then you can actually use the Stokes theorem, okay, which says that the line integral of f dot dr along the curve C, okay, if the curve C is closed and anti-clockwise, is equal to the Flux integral of curl f dot n ds. In the Flux integral is actually, you have here, okay, f, normally it's f dot n ds, Flux integral. Now the f become curl of f. So you have one more step, you find the curl of f first. Later on, you dot with the unit normal vector, okay, unit normal vector with your, okay, surface S. ds is 1 unit of the surface S. So Stokes theorem is actually 3D of Greens theorem. So remember, Stokes theorem is actually 3D of Greens theorem. Because, okay, Greens theorem, you can evaluate the line integral of curve which is in 2D. Then you find curl of f, because 2D, okay, this one, dot n ds is actually your dA. In 3D, 3D, okay, the dA here you need to, okay, dot with the unit normal vector with 1 unit of the surface area. So please take notes that Stokes theorem is 3D of Greens theorem. Curl, actually we have learned, okay, what's a curl, for learning the conservative vector field F. Okay, when F is conservative, then curl of F equal to 0. Here we recall back what's the curl of F. Curl of F is actually denoted by del cross F. If F is 3D, then the curl, then your del is actually del del xi plus del del yj plus del del zk. Cross with the vector F consists of mi plus nj plus pk. Okay, and then so the cross product, okay, of a vector, the resultant, okay, in a vector. So you have a component I, j, k. To get your component I, you cross, okay, your column I, then just left j cross k. This is actually j cross k. So you do your component I. So you have del del y, your p, minus del del z, your n. Okay, and for component I and for component j, you close j. So you have I cross k. Okay, I cross k, you get negative j. Okay, then copy it down. You have del del x, okay, this m del del zp. So for component j, okay, you have del del x, the p. Because this is minus, so become del del z, your m, minus del del p, your x. Okay, del del xp. Okay, for component k, close your component k here. Close it. So it become I cross j, you get positive k. So which is del del x your n, minus del del y m. So this is curl of F. Okay. In your conservative of vector field, you have to confirm that curl of F equal to 0 vector means each component I, j, k equal to 0. Okay, example 1, let S be the portion of the paraboloid z equal to 4 minus x squared minus y squared, where the z greater and equal to 0, oriented upward. Okay, you can use your right hand side, okay, where the thumb here, okay, your thumb represents the direction of your unit normal vector, and direction of the other finger will represent the direction of your curve C. Okay, if your unit normal vector is oriented upward, okay, then curve C is actually oriented, okay, anti-clockwise. Okay, anti-clockwise. Then the question 1 is to verify Stokes theorem. So mean you have to do both hand sides. If the fxyz is equal to 2zi plus 3xj plus 5yk. Okay, so this is a surface of paraboloid z equal to 4 minus x squared minus y squared, with the mean maximum point is 4. Okay, z equal to 4 minus x squared minus y squared. Okay. Projection of this paraboloid happens when z equal to 0, where you get, okay, when z is 0, you get x squared plus y squared equal to 0. Once you plug in z0 here, okay, these two terms we bring to the other side, you get x squared plus y squared equal to 0, which is circle with radius 2 unit. Okay, radius 2 unit, and then, okay, because your unit normal vector is oriented upward, okay, pointing up, using your, okay, right thumb pointing up, the other finger, okay, show the direction of your curve will be anti-clockwise. So the direction of the curve is actually anti-clockwise. So take note that, okay, how you use the Stokes theorem. S is a piecewise smooth orientable surface that's bounded by a simple closed piecewise smooth curve C with positive direction, means curve C must be anti-clockwise. Okay, if curve C anti-clockwise, then your surface S is actually oriented upward. And then we want to verify Stokes theorem. So first of all, we will do the line integral f dot dr along the curve C. Curve C here is actually circle x squared plus y squared equal to, this is equal to 4. X squared plus y squared equal to 4. Then, parametric equation for circle. Same with what you do in the polar coordinate, where we have r is 2, cos theta, you change it to t. So x is 2 cos t, y is 2 sin t, t will from 0 to 2 pi. In this way, your curve C will be oriented anti-clockwise. Because when t is 0, x is 0. And then when t, let's say t is pi over 2, cos pi over 2, you get 0. Means x move from 2 to 0. Because 2 cos t, 2 sin t. Remember in the polar coordinate, when t is 0, t 0, 2 cos 0, you have here 0. When t is pi over 2, 2 cos pi over 2. 2 cos pi over 2, you get 0. Means x move from 2 to 0. So which is oriented counterclockwise. Then from xy parametric equation, you put into the RT. Component I is actually the x parametric equation. Component J is a y parametric equations. And then you find dr, and you ddt, the RT. So ddt 2 cos t negative 2 sin t, ddt 2 sin t, 2 cos t. The curve is 3D, that's why component z is 0, because on xy plane z 0. So ddt is 0, you got 0. So dr dt, then bring dt to right hand side, so you get here. Then you evaluate f dot dr. So this is the dr. F 2z, I plus 3xj plus 5yk. Plug in on the curve C where z equal to 0. And then x is 2 cos t, y is 2 sin t. Then you find the dot product first. 6 cos t plus this one, component I 0 times this one, you get 0. Component j times j. And then lastly, component I you get 0, component k you get 0 until left the component j times j, you have 6 12 cos squared t. And change cos squared t become half. Cos squared t, you change it become half of 1 plus cos 2t. So half 12 divided by half, so it's 6 times 1 plus cos 2t dt. Integrate 1, you have t, integrate cos 2t, cos is sin 2t divided by 2. Plug in limit of t from 0 to 2 pi. So 6, you plug in t 2 pi, got 2 pi. You plug in sin 2 pi, you have 0. Plug in t 0, 0. Plug in sin by 0 also 0, that's why answer is only 12 pi. The question wants you to verify Stokes theorem. We have done the left side, which is line integral of f dot dr along curve C. By Stokes theorem, the line integral of f dot dr is equivalent to the your plug integral. However, the f here become the curl of f. So you need to find the curl of f first. So the f, you got 2zi 3xj plus 5yk. Finding the curl of f. For component I, you close it. So you have del y, del y 5y, del y 5y minus del z 3x for component I. So del y 5y, you have 5, del z x 0. That's why answer for component I is 5. Okay, for component J, okay, cross your component J, you left the other two column, which is I cross K. Remember, is negative J. Okay, then you have minus delta x phi y. You got 0. Okay, minus delta z 2z. So you got here minus 2. Okay, minus 2 times negative, so positive 2. Okay, this is component J. Okay, later on component K cross the component K, you leave I cross J. So you have delta x 3x, which give you 3. Delta y 2z got 0. That's why component K, the answer is 3. So the curl of f, you get phi I plus 2j plus 3k. So you got answer for curl of f. Okay, and you need the unit normal vector. To get the unit normal vector, you need the surface z. Okay, z in this case is a paraboloid equation, which is z equal to 4 minus x squared minus y squared. Then differentiate z respect to x, you get zx, which is negative 2x. Differentiate z respect to y, you get zy, which is negative 2y. Okay, so this is a curl of f. This is result of the curl of f. Okay, the dot with n, this is a unit normal vector, formula. Cause the curve C is actually counted anti-clockwise using the right thumb represent the unit normal vector. When pointing up, then the unit normal vector pointing up. Curve C is anti-clockwise. Look back the questions. Oriented upward. Unit normal vector oriented upward. So curve C is anti-clockwise. Okay. For the unit normal oriented upward. Okay. So you notice component K. K is actually unit normal vector for Z direction. So the n unit pointing up. Then this is a n pointing up, this is a unit normal vector when n is pointing up, so z is positive. If n pointing down, component I positive, component J positive, component K negative. Numerator is actually the normal vector. We want unit normal vector, that's why divide by magnitude of the normal vector. So this is actually the n. This formula is actually the ds. You have learned in the surface area of scalar field. ds, 1 unit of surface area, which is zx squared plus zy squared plus 1 dA over region R. And then this one, square root and this square root cancel. So we become dot with negative del z del x I, negative del z del y j plus positive k dA over region R. Then look back the del z del x that you obtain. Del z del x, you get negative 2x. Negative again. That's why you got positive. Because del z del x, you get negative 2x. So negative, positive. Del z del y, you get negative 2y. So negative, positive 2y. And then we find the dot product first. Dot product. So 5 times 2x, you got 10x. Later on, component J, you have what? 2 times 2y, you have 4y. Later on, you have 3 times 1, so plus 3 here, blue color. So now become double integral of 10x plus 4y plus 3 dA over region R. So look back the region R from your surface of paraboloid. Paraboloid z equal to 4 minus x squared minus y squared. the region R is, okay, is actually, when you press your paraboloid parallel with z-axis, you get the projection R on, okay, xy plane. Happen when z equal to 0, you have x squared plus y squared equal to 4. It's circular region. Then the evaluate your dA using polar coordinate, which is r d theta. So r in this case will be, okay, the r from origin, because of, okay, full circle, okay, from origin 0 until 2. Theta full circle, theta 0 until 2 pi. R 0 until 2. So that's why dA change to r dr d theta. Limit of r is 0 to 2. Limit of theta 0 to 2 pi. Okay, x change to r cos theta. Y change to r sin theta. 3 maintain 3. Integrate respect to r first. Don't forget outside we still have r here. So integrate tan r squared cos theta. So become tan r cubed over 3 cos theta. Okay, and don't forget the second term. Okay, multiply by the r. Okay, third term also multiplied by r before integrate respect to r. So 4r squared sin theta integrate respect to r. So 4r cubed over 3 sin theta. 3r dr, you got 3r squared over 2. Plug in limit of r from 0 to 2. So you plug in r is 2 here. 2 cubed is 8. 8 times 10. So 80 over 3 cos theta. Plug in r equal to 2. So 2 cubed you got 8. 8 times 4, 32 over 3 sin theta. So plug in r into 2 into the third term. So 2 squared 4. 4 times 3, 12. 12 divided by 2. Actually you have, here is 6. Okay, this one becomes 6. So, okay, lastly, integrate respect to theta. So integrate cos theta, you get positive sin theta. Integrate sin, negative cos theta. So integrate 6 respect to theta. You got 6 theta. Okay, plug in the upper limit of theta into each term. Sin 2 pi, you got 0. Cos 2 pi we have 1, so negative 32 over 3. Okay, so plug in 2 pi into 6 theta, you got 12 pi minus substitution of lower limit. Sin 0, you got 0. Cos 0, you have positive 1, so negative 32 over 3. So plug in theta is 0, you got 0. So negative 32 over 3 minus minus become positive 32 over 3. These two cancel out, so you get the answer 12 pi. Okay, 12 pi, which is tally back with what you obtained using line integral of f dot dr. So the same example, but this example they want you to verify Stokes theorem. So we evaluate using the line integral f dot dr, you get the answer 12 pi. Using Stokes theorem, when the line integral f dot dr is equivalent to the line integral curl f dot n ds across surface S. Okay, we also obtain the answer is 12 pi. Okay, the last example here. Okay. The second example, use Stokes theorem to evaluate the line integral f dot dr if f(x,y,z) is xzi plus xyj plus 3xzk. C is the boundary of the portion of the plane 2x plus y plus z equal to 2 in the first octant traverse counterclockwise. Okay, this is the the tetrahedron surface 2x plus y plus z equal to 2. Okay, to get the x-intercept, let yz is 0, 2x is 2, hence x is 1. Okay, that's in first octant. And then to get the y-intercept, let x and z is 0, that's why y is 2 here. And then to let the z-intercept, let x and y 0, that's why z is 2. And then the curve C is actually is a boundary of the portion of the plane in the first octane traverse counterclockwise. The curve C consists of C1, C2, C3 traverse anticlockwise. If you want to do the line integral, C here you have to break it becomes C1, C2, C3. You have to do it 3 times. If you use Stokes theorem, then you just need to evaluate the Flux integral of curl of f dot n ds across surface S. And this projection R, region R, is actually happen when when z equal to 0. When z 0, you have 2x plus y equal to 2, and y is equal to 2 minus 2x. This is the region R. And using the right thumb, cause the curve C anticlockwise. Direction of the curve is given by the other fingers. And if the other fingers anticlockwise, then the right your thumb shows the direction of your unit vector, which is pointing up. So S is actually oriented upward if C is oriented counterclockwise. Then we find the curl of F. In this case, so where the F you got xzi plus xyj plus 3xzk. So finding the component I, close your component I, then you left here delta y 3xz minus delta z xy for component I. Then for component J, component J, so you have I cross K, which give you negative J. So copy down these 2 columns. And then component K, close it, so you got transfer these 2 columns here. This is I cross J, get positive K. Then evaluate the determinant. You have here delta y 3xz. So when you delta y x and z constant, so this gives you 0. When you delta z x and y constant, so it gives you 0 minus 0, which is 0. This is for component J, you have negative. Delta x 3z. So you got answer is 3z because 3 and z is constant. Delta x 3xz, you got answer is 3z. Delta z xz, you have answer is minus x. So multiply with negative, that's why I have x minus 3z. Component K. Delta x xy, you have y. Delta y xz, you got 0. That's why answer is y. So curl of f we have obtained. This is 0i plus x minus 3z j plus yk. Curl of f. And then this is formula for unit normal vector which is pointing up. This is the n. This is a formula for 1 unit of surface area. And this square root and square root can be cancelled. So we need the del z, del x, del z, del y. So from tetrahedron equation, express a z as a title, you get z equal to 2 minus 2x minus y. Zx. Differentiate z respect to x, you got negative 2. So negative 2. Differentiate z respect to y, get negative 1. So negative, negative. This show the n. So that's why we have here negative multiply negative 2, you got positive 2. Negative multiply negative 1, so positive 1. For unit normal vector which is pointing up, component K is positive. For unit normal vector pointing down, component K negative. Component J, this is positive. del z del x, positive del z del y. Okay. So this is the curl of f dot with the normal vector dA. Okay, and then you do the dot product first. 0 times negative del z del x dot. Okay, 0 times 2. Yeah, 0, and then this one x minus 3z times y, that's x minus 3z. Lastly, y times 1, so plus y. Okay, dA over region R. Okay, region R, as shown just now, from the tetrahedron surface, 2x plus y plus z equal to 2. The region R is on xy plane, happen when z is 0. We have 2x plus y equal to 2, or y equal to 2 minus 2x. So since this is non-circular region, we solve it using Cartesian coordinate, and let's say we solve it using vertical bar, which is dy dx, then y touching the x-axis, which is y equal to 0, until the upper curve, which is y equal to 2 minus 2x. So this is the lower limit of y, this upper limit of y, and you're going to sum your vertical bar actually from left side, which start x0, until right side, which start x equal to 1. That's why your limit, x 0 to 1, y 0 to 2 minus 2x from here. 0, 2 minus 2x, x 0 to 1. Now become the problem of double integral in Cartesian coordinates. Okay. And then before you want to solve the double integral, z, make sure replace back z is actually 2 minus 2x minus y. Okay. Because from the plug integral, we reduce it to double integral, so the z you must express in terms of x and y. So this is the z, 2 minus 2x minus y. So we simplify first. So x minus 6, and then this one, negative 3 times negative 2x plus 6x. So negative 3 times negative y, so plus 3y plus y. Simplify it first, x plus 6x, 7x. So minus 6. So 3y plus y, 4y. Now integrate respect to y first. Okay, when integrate respect to y, you notice 7x minus 6 is actually constant. So that's why you have a constant time with y. Okay. So integrate, because 7x minus 6 is constant. Integrate constant respect to y, you have constant times y. So 7x minus 6 times y. Integrate 4y respect to y, you have 4y squared divided by 2, which give you 2y squared. 2y squared. So plug in limit of y from 0 to 2 minus 2x. You plug in into y here. This one. Okay, then this one. 2 times 2 minus 2x squared. And then if you're lazy to expand, you may just use your scientific calculator to evaluate from this line. Or you may expand it. Notice you have 2 minus 2x, 2 minus 2x. So I factor out 2 minus 2x, so bracket, multiply 7x minus 6 for second term, have 2. One more 2 minus 2x. And then expand the second term here. So you have plus 4 minus 4x, collecting the same term, 7x minus 4x, 3x minus 6 plus 4 minus 2. Okay. And then you expand. So you got 6x minus 4. This is minus 6x squared, and then plus 4x. Here we are collecting back the term. So minus 6x squared. So 6x plus 4x, 10x minus 4. We only integrate it respect to x. So you get negative 2x cubed plus 5x squared minus 4x. Plug in the limit from 0 to 1, we get the answer is negative 1. Okay. If you feel troublesome to integrate manually, actually from this step, you may use your scientific calculator. From this step, you may directly use your scientific calculator to give you the answer. You got 7x minus 6. 7x minus 6 times 2 minus 2x plus 2 times 2 minus 2x squared. 0 to 1. Straight away you get the answer negative 1. Okay, instead of collecting the third factor out, simplify, expand, lastly integrate, so long step you get negative 1. So in here we have illustrate the Stokes theorem using 2 examples. First example we show we prove the Stokes theorem left side, right side. Second example because in 3D space, then we just using the Stokes theorem. We conclude back what we have learned today, and in the last lecture of your vector calculus. The Stokes theorem actually is a 3D Greens theorem. Conclude back because the 2D Greens theorem is the blue color here, and then the line integral of differential form is actually equivalent to the line integral of vector field, and del n del x minus del m del y actually is equivalent to the curve of f. If the curve is curve is in 2D and curve C is closed anti-clockwise, then we can use Greens theorem, the blue color here. And we have proved that this del n del x minus del m del y is actually curve of f. So Greens theorem is for the curve which is in 2 dimensions, which is closed and anti-clockwise. Instead of evaluate it for piecewise smooth curve, for example, rectangular curve, we got 4 curves, C1, C2, C3, C4. You have to evaluate it 4 times. If the curve that C1, C2, C3, C4 close, it form region R, then you can use the Greens theorem. How about if your curve C, you want to evaluate the f dot dr, if the curve C is in 3 dimensions, like in second example here. C1, C2, C3. Then you have to evaluate it 3 times. Some more, to get the parametric equation in 3D. 3D. Then you have to evaluate it 3 times. So in this case, your curve C1, C2, C3 closed, it formed because it formed the surface. Because in 3D, only its projection give you region R. Curve C1, C2, C3 form a closed surface. The closed surface here, if your curve C is transverse anti-clockwise using your right hand, right hand, the other finger pointing as the direction of the curve, and the right thumb will show the direction of the unit normal vector. If the curve is transverse anti-clockwise, then the unit normal vector will be pointing up. So in this case, unit normal vector pointing up, n is pointing up. Then instead of evaluate the line integral 3 times, you just need to evaluate the plug integral 1 time. The plug integral 1 time. So the line integral f dot dr along curve C, if the curve is closed and anticlockwise, okay, it forms a closed surface S. Then instead of evaluate your line integral like the tetrahedron, okay, example 2, evaluate 3 times, you just need to evaluate the Flux integral. Okay, however, here is curl of f dot n ds, okay, across the surface S. Okay, curl of f, okay, is here. Curl is del del xi plus del del yj plus del del zk. Okay, the result is the vector. To get component I, close component I, you get here. J, I cross k, you get negative j. K, you close it. So you get I cross j, you get positive k. So you evaluate your curve first. Okay, evaluate your curve. Okay, so this is a curve. Okay, this is a unit normal vector which is pointing up. So component k positive, component j negative del z del xi, j negative del z del yj. Okay, the numerator is actually normal vector divided by its unit, so it gives you unit normal vector. Okay, this is formula for ds. So square root and square root cancel. So you have a curl of f dot with the normal vector dA over region R. Okay, because the curve is in 3D, so it forms a surface, and the surface, when you project it, you will get the region R. So depend on the region R. If circular, then you solve it using polar coordinate. If the region R is non-circular, then you solve it using Cartesian coordinate of either dy dx or dx dy. Okay, in example 1, we prove that Stokes theorem means we do it left side, right side. Okay, we do it both hand side. We do the line integral and we do the curl of f here. Example 2, because it's troublesome to do 3 times of curve 1, curve 2, curve C, we use the Stokes theorem means we'll do the right hand side curl of f. Okay, Flux integral of curl of f dot n ds. Okay, with this, okay, thank you for your attention and watching this video.